Welcome to G Fun Facts Online. Imagine holding a perfect, living digital copy of a brand new jet engine in the palm of your hand. Not just a 3D model, but a virtual twin that experiences the same stresses, the same temperatures, the same wear and tear as its physical counterpart in the real world. Now, what if this digital twin could not only tell you what's happening right now, but could also predict a catastrophic failure weeks in advance, from a signal so faint it's practically invisible? And what if it could help you design an even better engine, one made from a material that doesn't even exist yet? This isn't science fiction. This is the world of digital twins, and it's on the verge of a revolution powered by the strange and wonderful world of quantum mechanics. Today, we're diving into quantum-enhanced digital twins, or QEDTs, and how they are set to redefine what's possible in the world's most high-stakes industries. At its heart, a digital twin is a dynamic, virtual replica of a physical asset, process, or even an entire system. Think of it as a car's digital ghost. Sensors all over the real car constantly send data: speed, engine temperature, tire pressure, G-forces in a turn, to its digital twin living in the cloud. This digital twin isn't static. It's a living, breathing dataset that mirrors the physical car's life. This technology is already changing the game. Manufacturers can run thousands of what-if scenarios. What if we use a different alloy in the chassis? What if we push the production line 10% faster? They can test these changes virtually, gaining deep insights without the enormous cost and risk of building physical prototypes or disrupting a factory floor. This allows for predictive maintenance, optimized assembly lines, and faster product development. But as our ambitions grow, so does the complexity. The intricate physics of new materials, the mind-boggling number of variables in a global supply chain, or the subtle vibrations that whisper of future equipment failure. These are problems that are starting to overwhelm even our most powerful classical supercomputers. They hit a computational ceiling, unable to find the truly optimal solution among quintillions of possibilities. This is where we need a new kind of power. Enter quantum computing. Classical computers, the ones in your phone and on your desk, think in bits, either a 0 or a 1. They are incredibly powerful, but fundamentally linear. A quantum computer uses qubits. Thanks to a bizarre quantum principle called superposition, a qubit can be both a 0 and a 1 at the same time. And thanks to another principle, entanglement, qubits can be linked in a way that what happens to one instantaneously affects the other, no matter the distance. This allows quantum computers to explore a vast number of possibilities simultaneously. They don't just walk down one path to find a solution. They explore every possible path at once. This quantum leap in computational power is the key to unlocking the true potential of digital twins. When we fuse quantum computing with digital twin technology, we get the quantum-enhanced digital twin, or QEDT. This isn't just a simple speed boost. It's a fundamental transformation. It's like giving your digital twin a crystal ball that's actually based on the fundamental laws of physics. The advantages of this quantum enhancement can be broken down into three main pillars. The first pillar is unparalleled simulation and modeling. Quantum computers are naturally brilliant at simulating quantum mechanical systems. Why? Because they operate on the same principles. This means they can model the behavior of molecules and the properties of novel materials with a precision that is literally impossible for classical computers. For industries like aerospace, where creating lighter, stronger, and more heat-resistant materials is the holy grail, this is a game changer. Imagine trying to design a new alloy. Classically, you'd mix some metals, test it, see what happens. It's slow and expensive. A QEDT could simulate the interactions between atoms in millions of potential alloys, identifying the perfect candidate before a single gram of metal is ever melted. Companies like Boeing are already looking at quantum computing to design better corrosion-resistant materials, while Airbus is exploring it for hydrogen fuel cell propulsion. The second pillar is solving complex optimization problems. Many of the toughest challenges in manufacturing are what we call combinatorial optimization problems. That's a fancy term for problems with an astronomical number of possible solutions. Think about scheduling production in a massive factory, optimizing the routes for thousands of delivery trucks across a continent, or managing a global supply chain during a crisis. The number of possible combinations can be greater than the number of atoms in the universe. A classical computer can only check a tiny fraction of these, settling for a good enough solution. Quantum algorithms, like quantum annealing, are built for exactly this. They can survey this vast landscape of solutions and pinpoint the truly optimal one, the most efficient, the most cost-effective, the most resilient. This translates into massive reductions in production time, lower operational costs, and supply chains that can withstand unforeseen disruptions. The third and final pillar is enhanced artificial intelligence and machine learning. We feed our digital twins vast amounts of data, and we use machine learning to find patterns. But classical machine learning can miss the sneakiest patterns. Quantum machine learning, or QML, can supercharge this analysis. It can identify complex correlations in data that are completely invisible to classical models. This leads to what you might call precognitive maintenance. Instead of just predicting a failure based on historical data, a quantum-enhanced digital twin could detect subtle, physics-based anomalies, tiny changes in vibration, temperature, or energy consumption that signal an impending failure long before any traditional sensor would pick it up. It's the difference between seeing a storm on the radar and feeling a change in the air pressure before the clouds have even formed. So where does this technology matter most? In high-stakes manufacturing, where the margin for error is zero and the cost of failure can be catastrophic. Let's start with aerospace and defense. A modern aircraft is a flying city with millions of components, all of which must work perfectly under extreme stress. Boeing has been a pioneer, using digital twins for everything from design to in-service maintenance. A QEDT takes this to the next level. It could simulate the airflow over a new hypersonic wing design with absolute fidelity, or model the complex chemical reactions inside a next-generation rocket engine. The U.S. Air Force is already working with startups to use quantum computing to accelerate their modeling capabilities. The goal is to design, manufacture, and qualify safer, more fuel-efficient aircraft in a fraction of the time it takes today. Now let's look at the automotive industry, which is undergoing a massive shift to electric and autonomous vehicles. The challenges are huge. Designing new battery chemistries, optimizing wildly complex global supply chains, and, most critically, ensuring the absolute reliability of self-driving software. BMW is already creating digital twins of entire factories to simulate production. Tesla famously treats every one of its cars as a dynamic asset with a comprehensive digital twin in the cloud, allowing it to push improvements via over-the-air updates. With quantum enhancement, car makers can accelerate the discovery of new lightweight materials for better range, optimize factory workflows down to the second, and perform exhaustive virtual testing of autonomous driving systems in billions of simulated scenarios to guarantee their safety. Toyota has already used a quantum method to analyze all possible design structures for a component at once, finding the one with the best thermal conductivity, a task that would be impossibly slow using classical computers. A less obvious but equally high-stakes field is biomanufacturing and pharmaceuticals. Making advanced medicines is an incredibly delicate process. The tiniest deviation in raw materials or temperature can ruin a multi-million-dollar batch. In a recent award-winning research project, scientists used a quantum-enhanced AI system to create a high-resolution digital twin of a biomanufacturing plant. This system was able to spot tiny, previously undetectable defects in raw materials, preventing costly production failures before they started. In the pharmaceutical world, QEDTs could one day simulate how a new drug interacts with the biochemistry of the human body, drastically reducing the time and cost of clinical trials and bringing life-saving medicines to patients faster. This might sound like it's all years away, but pioneering companies are already getting real results. The automotive supplier Denso used a D-Wave quantum computer to optimize the paths of its automated guided vehicles in a factory. These are the little robots that carry parts around. The quantum solution cut the time the robots spent waiting for a clear path by 15%. That's a significant efficiency boost on a busy factory floor. In the energy sector, a company called Multiverse Computing developed a quantum-enabled digital twin to make the production of green hydrogen more efficient. By finding the optimal operating parameters, their system increased both hydrogen output and revenue by 5% compared to the best classical methods. And chemical giant BASF is using quantum computing to research new catalysts, while Daimler, the parent company of Mercedes-Benz, is using it to simulate new battery chemistries. Rolls-Royce, the jet engine maker, is exploring what it calls quantum-inspired algorithms to improve engine aerodynamics, hoping to find designs that create more thrust with less fuel. Of course, the road ahead isn't entirely smooth. The quantum computing hardware itself is still in its infancy. Building and maintaining stable, large-scale quantum computers is a monumental technical challenge. There's also a major shortage of people who understand both quantum physics and manufacturing engineering. And integrating these futuristic quantum systems with today's factory infrastructure is a complex puzzle. But the path forward is becoming clearer. We're seeing the rise of hybrid quantum classical systems. These use classical computers for what they're good at and offload the really thorny problems to a quantum processor. And thanks to cloud platforms, you no longer need to have a billion-dollar lab to access a quantum computer. Companies can now rent time on quantum machines, allowing more and more people to experiment and innovate. As the hardware matures and the algorithms get smarter, the impact will be profound. We're looking at a future of self-optimizing factories, where quantum-enhanced digital twins adjust production lines in real time to maximize efficiency and eliminate waste. The pace of material science will accelerate beyond our wildest dreams, creating materials with extraordinary properties we can't even imagine today. The safety and reliability of complex systems like aircraft and autonomous cars will reach levels previously thought unattainable. The fusion of the virtual world of digital twins and the computational power of the quantum realm is more than just an upgrade. It is a true paradigm shift. It's a journey that's just beginning, but one that promises to empower us to build a future that is more efficient, more sustainable, and ultimately, more intelligent. Thanks for tuning in to G Fun Facts Online.